Good morning. We're going to do some substitution rules here. I've just taken a selection of 2 from your homework problems and 1 not in your homework problems to work through these. All right, so when I look at this problem, I see secant squared as a function that's been squared. There's also theta times 2. So there's a few different guesses that you might think about for you. Perhaps you should be 2 theta. Perhaps you should be secant of 2 theta. If it was the first one, this would turn into secant squared of u. If it was the second one, it'd be u squared. And the proper guess of u is really going to be dependent upon what would substitute everything out. If I guessed secant of 2 theta, and I went to my du for this one, I know I would have to do secant of 2 theta, tangent of 2 theta, times the derivative of what's inside times 2. But I don't see any tangents in here, so I'm going to say that is not the proper guess. Instead, let's just let u be 2 times theta. If I were to do that, then du, the derivative with respect to theta, would be just 2. However, I'm going to write it as a differential and put the d theta on the right-hand side. Now, with constants like the 2, I might do one of two things. I could divide by 2, since there's no 2 with that d theta, to get d theta by itself, or I could prepare this integral by writing it like this, where I'm going to want a 2 times a d theta. So if I'm multiplying by 2, I've also got to divide by 2. Now, the way we've been doing it in class, though, is simply writing du over 2, or 1/2 du, equals d theta, since I have a d theta in this problem. All right, so let's color code this now. So I've got secant squared. Now 2 theta, I just called that u. And d theta, right here, is 1/2 du now. This 1/2, I'm going to bring it out in front of my integral because I prefer it there. Secant squared of u du. And this is something that we already know. So the 1/2 comes along for the ride. Secant squared is just tangent of u plus a constant. And we're very, very close to being done, except the u there is not what we originally had. We originally had this in terms of theta. So 1/2 tangent of 2 theta plus a constant would be the solution. You could verify this by taking the derivative here and seeing that it turns into secant squared, and by the chain rule, the 2 would cancel out the 1/2. Now this problem is a little bit interesting. We have a few different options. This is number 32. Let's get it over here in the corner. Perhaps u could be natural log of x. It could be sine of natural log of x. There's lots of options that you might guess. So trial and error. In this case, I'm going to go with the natural log of x. The reason for that is I'm looking and I say, well, I can already really recognize that this would give me the derivative of 1 over x dx. And I have that right there. So if I use that u substitution, it'd be sine of u. Let's keep it color-coded, sine of u. And then this stuff right here is just du. If I wanted to make it extra explicit, which I will do here, I can think about this as sine, before I do the substitution, sine of natural log of x. Times, I'm going to rewrite this as 1 over x dx. At which point you can now clearly see this is really sine of u du. And you know how to do that substitution or that antiderivative. Negative cosine of u plus a constant. Let's stick the u back in there as an x, and we get negative cosine of natural log of x plus a constant. And you're done. So really we're trying to undo the chain rule. Now let's look at this one. I haven't done this one yet myself, so let's think about this. I see an x cubed there. I have an x squared plus 1 on the inside. Now, it would be nice if it was just an x on the outside or a 2x, so that when I do the substitution where I'm going to guess u is what's on the inside, it would all work out so nicely. But let's see what happens here. So let's guess u as x squared plus 1. If that was the case, then du would need to be 2x dx. Now this is a little bit strange, but let's rewrite it this way. I'm going to finagle with my integral over here for a second. I want a 2 in there. So this x cubed, I'm going to take one of the x's and put it over here with the dx. Split that up. I want a 2 there, so I'm going to need a 1/2 to balance that out. Well, now I've made the du come alive right there. And then inside of this square root symbol, we have our u. I'm going to do this in 2 steps. So let me do it this way. I'll write it as x squared plus 1 for a moment here. Let's copy this down again. So the 1/2 comes along. Integral. I'm going to leave the x squared there for just a hot moment. I'm going to come back to it. The square root, well, we're going to stick the u inside of there. And the 2x dx turns into du. But what do I do with this x squared? Well, let's look at this u up there. I can actually rewrite this and say, well, if u is x squared plus 1, then u minus 1 is equal to x squared. So I'm going to actually replace that. So let's get rid of that x squared, and we're going to call that here u minus 1. All right, so why would I do this? Well, check this out. This is actually a lot easier to integrate because I can multiply this through. If I were to do that, this would turn into, well, u times the square root of u is u to the power of 3/2 minus 1 times square root of u, which is u to the power of 1/2 du. This is way easier to integrate than the original problem. The 1/2 coming along for the right. I'm going to use some nice big brackets. U to the 3/2 goes up 1 power, so 5/2. Multiply by that upside down to cancel it if I had to take a derivative. So there's the integral of the first one, minus, likewise, all plus a constant. I'm going to scroll down just a tad. Actually, let's zoom out a tad. Here we go. So now we're just going to substitute the stuff back in. So the 1/2 times 2/5 is equal to, well, 1/5. U is x squared plus 1 to the power of 5/2 minus 1/2 times 2/3 is 1/3. U is x squared plus 1 to the power of 3/2. And all that plus some arbitrary constant. Good, so I would have never, ever in 100 years guessed off the bat this hunk of junk as my original equation, but it turns out if I take a derivative of that, it simplifies down to that original problem up there of x cubed times the square root of x squared plus 1. Now that was a big long process, so you could always verify this if you need to. So you can be done with this video if you want. But I'm going to take a hot second to just verify that that is, in fact, what we get. So let's do that. So let's take a derivative of this just to see. So I'd have the 5 halves come down, so I get 1/2 x squared plus 1 to the 3 halves times the chain rule, so times 2x. Minus 1/3, I'm going to get 1/2 x squared plus 1 to the 1/2. Because of 3 halves and the 1/3, the 3's cancel, times chain rule times 2x. So this will give me x times this thing. But now notice I really want something with just a square root. So I'm going to rewrite this as x plus 1 times x squared plus 1 to the 1/2. So those together would be to the 3 halves. Minus, I'm going to rewrite this as x squared plus 1. So this here then gives me x cubed. If I put this in here, x cubed plus x, I'll write it as a square root x squared plus 1, minus x square root of x squared plus 1. So if I distribute that, this will cancel with this, and I'll just be left with x cubed times square root of x squared plus 1. So there's just a check. That checks out. We did it. All right. I don't know if this will help you, but hopefully there's a part of you deep down in your soul that it touches and says, oh yeah, use substitution. Don't gotta like it, but you gotta love it.